this video what we're going to do is look at how we can work out how much potential each half cell has towards creating a battery, so that we can find combinations that are going to give us the voltage that we want. To do that, we need to know each half cell, what it is going to contribute, and in order to figure that out, we need to be able to measure it against a standard that we're going to say is the zero value. Okay, so the standard electrode potential of a half cell is going to give us this measure of its tendency to lose or gain electrons. We can't measure that on its own because it's only half of a cell. You need to have a circuit for electrons to flow, so we're going to use a primary reference. And the primary reference for measuring standard electrode potentials is the standard hydrogen electrode. And by definition, and if they ask you why the value of this is zero, you say by definition, we've decided on an arbitrary scale, by definition, this one is 0.00 volts. So just like in the degree C scale, we've decided that water freezing is 0 degrees C and everything else is relative to that. The zero it's just arbitrary. Why water freezing? Well, that is just where they set it. So by definition, this is 0. What does this half cell look like then, this standard hydrogen electrode? So it's a little bit special. We've got to have the two species from the half equation, that's the rule for half cells, the two species from the half equation in our beaker. But let's have a look at the half equation. These are provided to you, remember, in your exam. You do not have to memorise these. So we've got 2 H plus ions AQ, pick up 2 electrons to form hydrogen gas, and remember that they are always written as reductions in these series. So it looks like that. That's our equation. So we need to put these two things in our beaker. So I need to put this in the beaker, I need to put this in the beaker. So this one's, the hydrogen ions have got an aqueous state symbol, so they're going to go in the beaker here. 1 mole per decimeter cubed H plus AQ. Now what could that be? That could be HCl. If it was going to be H2SO4, could you think what concentration it might need to be to give you 1 mole per decimeter cubed of H plus? What concentration of HCl? Now this funny little chimney thing is about having a way to bubble the hydrogen gas into the water and make it touch the electrode, which is where the electrons are going to move. We need there to be surface contact at the electrode of hydrogen ions and hydrogen gas. So this funny little chimney is about pumping the gas in at the pressure for the gas, which is 100 kilopascals. Hydrogen gas is going in there. Now we've got no metal in this equation, and when we have no metal we need to use an inert, unreactive metal as our electrode, so we use a platinum electrode. So what are the key features? We've got hydrogen gas at 100 kilopascals, so your diagram needs to include that. We've got H plus ions, AQ, at 1 mole per decimeter cubed. So we could be, e.g., 1 mole per decimeter cubed HCl, or what would it be if it was H2SO4? We'd have to be 0.5 in order to end up with 1 mole per decimeter cubed. Then we've got a platinum electrode, because there was no metal in our half equation to conduct the electrons out into the wire, so we needed to use an inert metal, and we're going to use our other final standard condition, a temperature of 298 Kelvin. This is what we're going to connect each thing we want to measure to, because this has a value of 0, so we're going to be able to find out the value for our other things. So what is standard electrode potential? Standard electrode potential is the EMF of a half cell compared with a standard hydrogen half cell at all the standard conditions. So 298K, 100 kilopascals, concentration 1 mole per decimetre cubed. And we find it by measuring against hydrogen. So let's have a look at that, putting that into practice. How would we find the amount of that 1.10 volts that we measured in our first battery we made? How much of that was due to copper? So to find that out, we put copper on one side and hydrogen on the other, and we're going to find out how much of the 1.10 volts comes from copper, because we're setting the 0 for the hydrogen, so how much of it is going to come from copper? Now, first thing we have to do is write an equation for that half cell. So they're the two species, copper 2 plus and copper. Remember that the equations all are written as reductions. So how would we do a reduction there? Is it copper 2 plus becomes copper? Is that reduction, or is it copper becomes copper 2 plus? So we've written down our half equation as a reduction. It might not happen as a reduction at the end of this, because we might not be the positive electrode at the end of this, but if it is, it will be a reduction, and if it ends up being the negative electrode, it will be an oxidation. So here we go, we've got our cell. We've put the hydrogen one on the left, so let's see if you can remember how to label the parts. So what are going on these two arrows? What's going here? What's this label? What's this? What would be here? Okay, so see if you can label any of that. So if you've managed to label it, it should look like this. You've got the voltmeter at the top there. We've got on the left hand side our standard hydrogen half cell, and on the right hand side we've got the copper half cell. Now if you do go back and look at the bottom of page 5, our convention for these is always, with the standard hydrogen electrode, is always drawn on the left. That's the convention for the standard hydrogen electrode, and the other electrode is drawn on the right, so the other half cell is drawn on the right. When you set this up and you connect it to a voltmeter, so you set up all these beakers and you set up the hydrogen gas and you pump the hydrogen gas in, then the voltmeter reads 0.34 volts. And in order to ensure that that reading is positive and not negative, you have to have the copper connected to the red wire. So you see that whenever you're getting a positive reading, copper is connected to the positive terminal, which means that the copper is the positive electrode, because it's on the positive terminal. Therefore, we're reading 0.34 volts, therefore the voltage is 0.34 because the other one's 0. And the electrons, remember our star box again, you need to go back a page. What did it say about where oxidation occurs and where reduction occurs? Reduction occurs at the positive electrode, so electrons have to flow there for them to be gained. So they're going to have to flow to the copper from the hydrogen electrode, or the platinum of the hydrogen electrode. So the electrons are going to flow from the platinum electrode of the hydrogen half cell to the copper electrode of the copper half cell. So the bits of metal are going to flow, if we draw that on, they're going to flow in this direction, so that reduction can occur at the copper half cell.